Let's look at an example design using Bode. So let's say we have a transfer function for our plant, g of s. G of s has a pretty big gain, 3, 4, 3, 8, 1, over s times s plus 15.5 times s plus 35.5. So the goal of this example is to design a lead compensator I'm going to call it D of S, and I want D of S to produce the following properties. So I'd like to have phase margin at the end be about 52 degrees, and I'd like for my gain margin to be equal to 4.4. So in the end, I would like to verify this using MATLAB. So the MATLAB that actually implements this and shows you how to use the various commands is up on the web page. But you should be able to come up with it on your own and then just compare that. So take a few minutes, go back and look over the lecture that talks about how to achieve a particular gain margin and phase margin using lead compensation. Pause this video and then come back after you have your solution and you can compare it. Okay, so how does the solution look? So the solution is that we'll use MATLAB's margin command. So with the margin command, using our open loop transfer function from above, the margin command gives us the existing phase margin equals minus 5.235 degrees, and that the gain margin is equal to minus 1.76 dB. So, by the way, the phase margin is at 25.9 radians per second. And minus 1.76 dB, the gain margin is at 23.5 radians per second. So by looking at these two numbers, you can see that this is unstable in the closed loop. And that's because you want phase margin to be greater than 0 and gain margin to be greater than 1. So, with MATLAB, we can see that our omega c comes from here, 23.5 radians per second. And our goal is to get phase margin equal to 52 degrees. And so we calculate the gain that we need, 52 minus 5.235 gives us about 57.2 degrees. This is how much we need to increase our phase by. So in order to get this kind of an increase, we know the frequency at which it happens. 23.5 is where our omega c is. So let's go ahead and apply the design techniques that we've seen how to use. So I'm going to let d of s equal some k lead times s over a plus 1 over s over b plus 1. And I know that a over b is going to be equal to 1 minus the sine of our increase over 1 plus the sine of our increase. So I'd like to keep omega c at 25.9 radians per second. That's where it is. The other was not the crossover frequency, it was the frequency, if we go back and look at this page. So the gain margin is at 23.5 radians per second. That's where phase crosses minus 180 degrees. So we'd like to keep the phase margin happens at 25.9 radians per second, so we want to keep omega c equal to there. Phi max is equal to 57.2 degrees. So that gives us, if we remember that omega c should be equal to the square root of a times b, we can now calculate the ratio of a over b. Such that d of s at s equals j square root of ab equals 1. Or in this case, d of s equals the square root of b over a times s plus omega c square root of a over b and s plus omega c square root of b over a. So in doing this, you'll add these various commands to MATLAB. Calculate the ratio of a over b by multiplying the sines and the cosines, or the sine and then subtracting the sine on the other part. And so after you do that, you'll find that the b over a and a over b ratios, so the square root of b over a in this case turns out to be 3.4, and omega c square root of a over b equals 7.62, and omega c square root of b over a equals 88.1. So our controller d of s is equal to 3.4 times s plus 7.62 over s plus 88.1. So if you add d of s to GOL and then check MATLAB to see what the answer is using margin this time, you should get a phase margin equal to 52 degrees and a gain margin equal to 12.94 dB, which equals 4.4.